Welcome everyone to our group presentation for EME 521. Nicolas, Amir, and myself will be discussing Smooth Particle Hydrodynamics, a computational method for simulating continuum media. The presentation outline will be as follows. We'll start with a brief introduction and lead into the historical perspective of the method. Nicolas will then present the general principles and governing equations. Amir will follow by walking us through a hand calculation and numerical example. He will then discuss useful applications and will conclude with a brief summary. Computational fluid dynamics, or CFD, is a method used to translate the mathematical representation of physics of a medium, fluid in this case, to a computer model that can represent fluid in motion. CFD dates back to the early 1800s when the Navier-Stokes equation was derived. Before computers, these solutions could only be used for simple geometries and solved analytically. Today, we use computers to discretize the Navier-Stokes equation and solve more complex systems. CFD methods create a bridge from continuum to discrete. It is not possible to describe a fluid at every point exactly. Smooth particle hydrodynamics is a relatively new CFD method that is Lagrangian and mesh-free. Let us first briefly touch on the difference between Lagrangian and Eulerian. In Lagrangian, each particle is described at each point in space, or in other words, moving with the fluid. As you can see from the first image in this slide, the Lagrange observer is moving with the velocity of the fluid, where the Euler observer is describing the rate of change in one point in space. However, in both instances, they are describing time derivatives. The Lagrange derivative is velocity dependent. The Lagrangian method is also intrinsically mass conservative as shown by the bottom figure, which is not necessarily true in Eulerian. The resolutions of a Lagrangian method follow mass, not volume. So what would be the advantages of SPH? First, it is critical to understand that the best method is relative to the application. All methods have advantages and disadvantages. Some of the main arguments for use of this method are that it simulates highly dynamic and violent flows. It deals well with free surface flow, multi-phase flow, and complex geometries such as gearbox fluid movement. Since SPH is meshless and no calculations of fluxes are necessary, complex moving geometries can be accurately simulated. Just as there are advantages to the SPH method, there are also some disadvantages. SPH is relatively new, so developments are still ongoing. In SPH, physical quantities are computed by an interpolation of the quantities of the nearest neighbor. This results in slower computation compared to other methods. Boundary conditions are also hard to implement. They do not appear in natural ways, and when the particles approach a solid boundary, they can create unrealistic interactions. Another noted issue with the SPH method is tensile instability. This occurs because of the dependence on distance of the particle interactions. This will present itself as a bunching of particles. Computer simulation of physical phenomena has been an important part of engineering and science over the last several decades. It is a method used to test theories and hypotheses. Mesh-based methods such as finite difference method, FDM, finite volume method, FVM, and finite element method, FEM, apply to many areas of what we now call computational fluid dynamics or computational solid mechanics. These methods shown here have proven to be very practical for solving differential or partial differential equations of the physical properties of matter and energy. Simple geometries are solved easily with FDM, where FEM is mainly used for fluid flow problems, and FEM has always been useful in solving problems with complex geometries. Grid-based numerical methods discretize or divide a continuum into small subdomains by use of a mesh. The individual grid points are connected by this mesh. Some of the newer, less conventional methods are finite element discrete element method, or FEM-DEM, extended finite element method, the EX-FEM, phase field methods, and boundary element methods, BEM. Extended finite method was developed to help solve problems with localized features, for example, the modeling of fractures. This does not require that the mesh be updated to track the path of the crack. The boundary element method, on the other hand, attempts to use a given boundary condition and fit those values into the integral equation. Then the integral equation is used to calculate the solution at any point in the interior. This method is specifically useful in simulating adhesive contacts. Smooth particle hydrodynamics has been around for over 40 years, but it is referred to as a new method. The method was invented in 1977 by Lucy Ginghold and Monaghan for a specific set of astrophysical problems in three-dimensional space. In the early 90s, as the need for the use in engineering applications presented itself, SPH was used for modeling of viscous flow and strength of materials. In the early 2000s, this method was heavily used in computer graphics. Today, this application is still evolving and becoming more and more widely used. Nicolas will now present on the mathematical foundation of SPH.
Now, we are going to review the mathematical foundation behind SPH. So, I will explain the mathematical artifacts that explain how SPH works, and then we're going to apply those artifacts to the conservation equations. So first, I want to give an idea of what is behind SPH. So maybe you already have an idea. I want to reinforce that by saying that the core of the SPH is an interpolation. So we can look at the picture to the right, which is a sketch of a domain. And that domain is full of locations where we know some properties or where we know a property A. Those points are the blue circles. And but also we are interested in compute that property A in other locations that are the red X. So to carry on this computation, we can relate the variable A to the neighborhood, to the neighbors, to the X locations. So this sounds arbitrary, like how big the area of influence is for a particular location. But the solution to this problem is given by the kernel, that is a mathematical function that tells how that area, how the weight of each point changes inside the area, and the area is given by the support hi that I'm going to explain. But the picture here is when the support is larger, so more points are influencing the variable a at the location x. If on the other side h becomes smaller, so the area of influence is smaller, and thus less points are impacting the value of a at the desired locations. So we have to take into account that SPH always needs to compute the points in the proximity of interest. So here is a general principle. If we were to solve this problem in the general case, in a continuous domain, we have the integral to the left. The value of variable a at x, okay, at the position x, that is a vector here, will be the integral over the domain, and of the variable a at those locations multiplied by the weight of those locations in our integral. However, uh, we as we have a discrete representation, we will have a discrete equation. But before going to that point, let's look at the compact kernel W. I told you this compact kernel determines the size and weight inside the effective area. So this kernel can be any function as long as it holds true some requirements. The first one is that this is a resemble of a probability distribution function. So the integral over the domain of the kernel must be equal to 1, right? Again, because this is a weight, this is a normalized density in the domain. Also, if our support H tends to 0, this kernel should converge to the Dirac distribution. What this means is that in a continuous domain in which, let's say, we know all the values at every location, if we were to pick a particular point arbitrarily and to apply this formula, if we have a H equals 0, that means that the value of the interpolated A is equal to the value of the property at that location. And finally, the last property is that the kernel must converge to 0 if the distance between 2 points exceeds a certain value. And this is the full idea of SPH. We don't need to know all the value of all the neighbors for a particular point. We only need to compute the neighbors inside the area of influence that is given by H, right? In SPH, it is useful to find this Gaussian kernel. It's in fact, at least for me, the most intuitive kernel to use, but there are also other kernels like cubic splines. Those are used because they help to correct instability problems. They may be faster, but they are not that intuitive. Instead, a Gaussian kernel, you can see this kernel like a bell shape around the x location, and then as it is an exponential, it converges to 0 after the distance d reaches certain value. Or not 0, but virtually 0 to be precise. So finally, we don't have a continuum in the domain. We have some particles that are, let's say, flying around, flowing around. So we need to convert the integral to a summation. So this is done by, if we know the mass of a particle and its density, so we can take an average of the variable a. That in this case, a will be an intrinsic, sorry, intensive variable. Uh, so this is the equation for SPH. This is the core of SPH. Now we are going to take this approach, this expression, and plug it into the conservation equations. Uh, but before going there, let's talk about some properties of this interpolation. So the kernel, this kernel, those kernels, and this expression allows for computing gradients directly without taking gradients in the kernel and not in the variable. This is a huge advantage that SPH has compared with other methods that also needs the gradients. This implies to make some interpolations spatially to compute this gradient, but in this case, the computation is directly. And if we already know the value of the area of interest for a particular point, so we can compute the gradient for not extra cost. That's the important part of this method. For example, in the case of the Gaussian kernel, this gradient is very straightforward to compute. As you see, it's also only a function of the locations and of the value of the kernel itself, and of course of the compact support H. We can apply the same operator for a vector field, and then this is not, that wouldn't be a gradient, that would be a divergence operator, and the same concept applies. However, this has showed some problems in terms of stability. So to correct the expression, let's look at the first line. Here we can take the divergence of an scalar property multiplied by a vector. So by the rule of the derivative of product, we have that this is our vector dot product with a gradient of a plus the value of a taken at a here, the a lowercase a is a location where we want to compute this gradient, this divergence operator, sorry. And so this VA means the velocity vector at location A. So now we can take the to the left what we need to compute, that is the gradient of the velocity, the divergence of the velocity field. So we have this expression to the right. With this expression, so we use the above definition. So in this case, for example, we replace V by uppercase A times V. So we have it here, minus BVA, and then we apply the previous formula for the gradient of A, of the uppercase A. We have it here. Finally, if we can see all the terms are the same. In fact, this VA does not depend on B. B are the neighbors. So we can take the velocity in, and all the terms are the same inside the summation. So we can express this divergence as this equation, right? And the only thing we have to do is to divide the right-hand side by A, uppercase A measured at A, and then we have the divergence. This is really important for the developing of the governing equations. Well, now in the Lagrangian framework, this is the expression for the mass conservation. We have that the material derivative is equal to minus density times the divergence of the velocity field. So, for example, when we have then a incompressible flow, that means the density doesn't change with time. That is why then this collapses to the divergence of the velocity field equals 0. So many of us may be more used to the Eulerian approach, where we have the partial derivative with time, partial derivative with location. But as SPH is evolving particles in space, so we have a Lagrangian expression for each particle. Uh, then the derivatives we just have here uh, is the evolution of each particle in time, and then we replace our divergence operator, but by the expression we had before, as we have the density as our variable A, so this cancels out, and we only have here the mass of the particle B. I hope this is being clear. Also, we can have an expression for the density directly, not the evolution in time, but only the density. And if we go to our definition of A, we can see that if A is the density, this collapses, cancels out, and we have the mass of V times the kernel function. That is just what we have here. It's the mass of every particle V times the kernel function. Well, now with the momentum conservation, the Lagrangian form is as follows. We have the material derivative of the velocity. It's We can see this like a summation of forces. It's the conservation of momentum sort of resembles the second law of Newton. So we have the acceleration. It's equal to the net force that is given by the gradient of pressure, uh, divergence, divergence of the stress tensor, or I don't know if that's exactly the term divergence, but this is a tensor, and then the nabla operator gives us a vector as well, and then the body forces. This as the stress tensor represents the surface forces. Well, we cannot plug directly the value of our forces here, and now we need an expression, the gradient of the pressure, and for the gradient of the Laplacian of the velocity. For the pressure, I'm not showing this here. This is a procedure that is quite similar to what we did before, but instead for the velocity, the divergence of the velocity. But if you see, instead of having property A multiplied by V here, we can have the same expression, the gradient of density of pressure over density. And after replacing some values, you can see that the expression takes this form. And this form is desirable because it's symmetric. If you can see the particles I, A interacts with B in the same way that B interacts with A. This is really important to conserve momentum, in the simulations. And this is the expression for the Laplacian. Beyond looking at the demonstrations of this expression, the important part is that all these values, see what is inside. If we want the Laplacian, we need the viscosities that may be constant, maybe not, uh, depending on the particular application. But those are dependent on pressure and temperature. Uh, so we have the density here, but also depends on pressure or temperature. The distances are known, at least in an explicit scheme, are known, and the velocities. So here, this is the important part also of the simulating fluid flow with SPH is that we need to couple the density and the pressure for these two operators. And then we have to plug an equation of state. Before going there, so I just want to say there are several ways to write these operators. We can also take the derivative, the gradient of B over rho square, rho cube, and then just provide a different expression for this. Uh, Now, to decide which one is the correct one, there is not a correct one. So to decide which one to use, so we have to see how much computational overhead we are putting into our software and how much instability we are solving by applying these more stable schemes for the gradients and the divergence operators. Well, so as I said, we need some constitutive equations to have a closure in our problem. Uh, so, for example, one that was not said, was implicit, is that we were talking about a Newtonian fluid. And that is why we could express the stress tensor as the viscosity times the Lagrangian of the velocity. Uh, this is one of them. Also, there are other ones like the equation of state that relates pressure and density. In the bibliographic review, the bibliographic review, we saw most of the time all the papers use the polytropic equation of state. This is suitable for weakly compressible fluids, but not many times we could find papers talking about equations of state, cubic equations of state. So this may be maybe an application that is still not very studied in the maybe for reservoir engineering. And our assumptions is we are going to explain this is the boundary conditions are are complex in SPH, and in Porous Media we have boundaries all the time, almost every application. So maybe SPH is not offering any advantage over other Eulerian methods, and maybe we have more uncertainty on those applications, and so that is why that area of application has not been develop, and then that is why we don't find many cubic equation of states being applied in SPH. We need to further investigate this, but in our reviews, this is what we could infer from the type of papers that are out there. Well, finally, sometimes we need to include artificial viscosity. Viscous dissipation is needed to model shock waves. This is beyond the topic we want to talk here. But the point is, and this happens with all the methods, we need to be sure what is our applications to come up with some constitutive equations. This one in particular is for the fluid flow. Well, finally, we have a general procedure. We have to populate the space with discrete particles. We need to compute velocity changes with the momentum equations. We can update the positions knowing those velocities, right? And we can summarize this as every time we have solved for a location of our particles, we can compute any other scalar property or even vector property. But once we update the location, we have the properties of the next time step. And then, for example, updating density gives us pressure in an isothermal condition. This is not the procedure that is usually taken. There are more complex procedures that may seem like different interpolation schemes in time, similar to, I would say that they are similar to Crank-Nicolson procedures in which you are interpolating between time n and time n plus n, 1, the next time step, or where you are computing an intermediate time step, and based on that intermediate location in time, you compute the variables at n plus 1. To summarize, to finalize the explanation of the foundations, it is important to talk about boundary conditions that are imposed in SPH. And the main problem that arises in boundary conditions is the area of interest that is given by the kernel function gets truncated for particles that are close to the boundary. And this is why SPH has been applied to problems in astrophysics, because there are no boundaries. And those are problems where we have large deformations, so it doesn't matter how far the particles go. Instead, for fluid flow, we usually have solid boundaries with non-slip conditions, so we have to solve how not to truncate this kernel function. And this is done by adding some edge and dummy particles across the boundaries, what increases the computational cost. But the goal here is to provide support, that is the expression, for those particles close to the boundary. And then we have to impose the properties of the variable, the particles at E1, E2, E3, and so on. Which information we have to provide? Well, that depends on the type of boundary. If we have a non-slip wall, well, we usually will impose velocity 0. Newman or Dirichlet's known pressure velocity respectively. So it depends on the type of boundary condition. And the point here is we need two sets of particles, one set that goes across the boundary, and those variables depends on the dummy particles that have to fill the space, the maximum area that the particle will try to look for in an interpolation.
In this part, we present some numerical examples for SPH developed in Matlab and Python environments. We will use some codes in both Matlab and Python environments to show how SPH can be used to simulate some typical examples in real world. So let's look at an example in Matlab environment. For the input data, we first set the simulation parameters. First, we set the time at which simulation ends, then the time step, and then particle mass, smoothing length, equation of state constant, polytropic index, and damping. In the next part, we create particles and define their initial locations, and then, according all the aforementioned, we define the number of particles and then log all position data during the simulation. Then we do sorting based on the distance of each particle to the origin, and then update densities, pressures, accelerations using the Sph equations, and then at the end we store the results for animation purpose. So when we run this code for different number of particles, we see that how the defining different number of particles can show us how this can be this can help us to simulate some typical examples in real world. So by increasing the number of particles, the more particles we consider, the more it becomes sensible and it becomes close to a real world examples. So from here we can understand that SPH, one of the applications of SPH, can be the simulation of slope stability analysis in, for example, dam construction in mining areas, in the surface mining, and also in dam construction, dam failure, and this type of examples in real world. So it shows us how SPH can be used in those fields. And then for Python environment, as you know, for Python we can develop packages for Python. For SPH, there is a specific package developed for Python which is called PySPH, a Python-based framework for Smooth Particle Hydrodynamics. So this PySPH package includes all the algorithms and all the equations of SPH, and the user can define any example, any problem of interest, and then solve it in using SPH simulation. The mechanism is that we create the particles, and then using the NumPy package and also PySPH particle array, we construct the solver using the PySPH solver and application integrator, and then we add operations and equation list, and then we solve the problem to simulate the example that we aim to simulate using SPH. This is how PySPH works. A typical example of this is simulation in theoretical astrophysics. In theoretical astrophysics, we can use PySPH, SPH in the form of PySPH package in Python to simulate star formation. So this example shows how SPH can be used in theoretical astrophysics. But the basics and the definition of the problem and the definition of the particles are similar to the example that we just presented for the Matlab example. The input and how to define the input and the particles, and how to update densities and accelerations, etc., are all similar to that example. But the different environment, that one was in MATLAB environment, and this is Python environment. In the Python environment, it is more close to the, it is a advanced level programming language. It is more close to the language we speak. So it is more easier than MATLAB or the other environments. So we can easily simulate the problems of interest using PySPH package in Python. So let's look at an example application for SPH. One example is the SPH can help us in real-world examples is bubble particle collision kind of fluid dynamics in Franz flotation. So Franz flotation is the process which is used for the separation of particles, mineral particles. It has different applications actually. One of them, or most commonly used application, is the separation and enrichment of mineral particles, valuable minerals from gangue minerals, where we have particles and then we in an environment, in an aqueous environment, also we have bubbles. So these bubbles, when they generated, they collect the hydrophobic particles and separate from the hydrophilic particles. So the collision, bubble particle interactions and bubble particle collision and the attachment of particles on the surface of bubbles and the efficiency of this interaction is so important in Franz flotation and the efficiency of Franz flotation. One of the applications of SPH can be to understand, to simulate these bubble particle interactions in Franz flotation. As we can see here, it shows us how to simulate the fluid flow around the bubble with different bubble sizes, and also velocity around the bubble with different bubble shapes in Franz flotation environment. So it starts, the algorithm is that it starts with force calculation and then calculate fluid motion by solving SPH governing equation, and then calculate forces acting on particles, including drag force using relative velocity to liquid, then contact forces if overlap occurs, and then interaction forces if necessary and applicable, and then calculate of particle motion by solving the EM governing equation, and then force calculation at the end. And then we do an iteration by adding dt into the time, and then t equals t plus dt. So we iterate this algorithm and then simulate the bubble particle interactions in Franz flotation. This is so important, and these insights that SPH can give us would help us to understand what happens in Franz flotation environment and how these particles and bubbles interact with each other, and how this particle moves, and the hydrodynamics of the process, and we can predict the efficiency of the process and figure out how to enhance this efficiency by generating different shapes of particles or different size of bubbles and shapes of bubbles, or the viscosity and the properties of the surrounding medium, in order to manipulate the hydrodynamics of the process. So in summary and conclusion, SPH is a computational method used for simulating the mechanics of continuum media, such as solid mechanics and fluid flows. SPH is a mesh-free method, which makes it ideally suited to simulate problems dominated by complex boundary dynamics like free surface flows. It has been used in many fields including astrophysics, ballistics, volcanology, and oceanography. It is a mesh-free Lagrangian method where the coordinates move with the fluid. Setting boundary conditions in SPH, such as inlets and outlets and walls, is more difficult than with grid-based method. This is a limitation for SPH method. This is partly because in SPH, the particles near the boundary get their kernel truncated, and this can be considered as a limiting factor for SPH compared to the mesh-based methods. So at the end, I want to thank you all for your attention and time, and I want to thank my team members, Cheryl and Nicolas, for all their efforts in putting together everything and finalizing this project. And we learned so much by working together and by working as a team, and we were able to successfully understand what SPH is and its advantages, its limitations, and how it can be employed in real-world engineering examples to solve some complex problems. Thank you all very much.